Okay, so lesson 2, we are looking at more of, basically application-based stuff here. And so we are back to the topic of straight line motion. We've already visited this topic multiple times this year. It keeps coming back, especially with derivatives. So in Unit 2, Lesson 7, the big ideas of position, velocity, acceleration were introduced. Particle motion problems deal with motion along a straight line. Could be horizontal, could be vertical motion of a falling object. It's important to note that this motion means the particle is moving along an axis, not along the graph of a function. So it's moving along that horizontal or vertical line. Now, this page is just vocabulary terms. It's a good reference page. That's what it is. It's a really good reference page. Some of this is going to be old hat. Some of it might be a little new, depending. Position. Often you'll see S of t, but you do sometimes see x of t or occasionally y of t, all based in t. Average velocity. Average velocity is like AROC. Okay, so average velocity over an interval a to b. In order to find your average velocity, you're using the change in position over your change in time. Okay, or notice they use the word displacement. And so position minus position over time minus time. Instantaneous velocity, so now we're talking IROC, that is your actual derivative because it's the rate of change at that instant. And so that is S prime of t is the best way to probably think of it. It's also definition of a derivative. And that's what that limit is definition of a derivative. Speed. Remember we talked about speed? Was it last unit? Unit before, I guess, probably. And speed is the absolute value of velocity. Speed is always a positive value. It can't be negative, whereas velocity can be negative. Acceleration, I think of it as the second derivative of position, or it's the derivative of velocity. Either way, that's all information saying that. Displacement over an interval. So that is ending position minus beginning position. It's the difference in distance from start to stop. It's not how many feet you traveled to get there. It's how far from the starting point to the stopping point. Okay, so in other words, you don't count all the forwards and backwards. Distance traveled, officially some of the absolute values of the distances between turning points. So that is, okay, we go forward 5, back 3, forward 5 more. That's adding up all of those values in the positive format, of course. Free fall motion. Okay, this is our basic formula setup, and you'll usually be provided a formula in a scenario. I don't feel like they usually make you create the formulas, like at least in a free response scenario here or anything. So S of t, negative 1/2 gt squared plus v naught t plus s naught t. So g being your gravitational factor there, v naught velocity at time 0, and s naught position at time 0. Okay. Direction changes. When velocity changes from either positive to negative or negative to positive at a point, velocity does not need to pass through 0 or even to be defined at a point where its sign changes in order for direction to change. Okay, so direction, I guess I read that kind of weirdly. Direction changes. When velocity changes from either positive to negative or negative to positive, that insinuates a direction change. Okay, and velocity does not have to pass through 0 or even be defined at a point where its sign changes in order for direction to change. And then, as we talked about before class, gravitational constants. Either 9.8 meters per second squared or 32 feet per second squared, depending on the scenario. I will say, watch for labels within a problem, right? I don't remember if there's necessarily tricky ones today, but we do have to watch for it. Okay, so these notes are basically, well, 1, 2, and 3 are all just big long stints that, you have all the different parts. Okay, so our focus here is to make connections, transitions between position, velocity, and acceleration. We've already done some of this, but it's, putting it more together. we're going to start with an algebraic numerical problem. We're going to do a table problem. We're going to do a graphical problem. So
it's going to be moving to the left.
I haven't even looked at the problem, dude.
Well, because you're going to get the derivatives, and you plug 0 in for t, all the t's are going to cancel out. So.
Example 1. A particle moves along the x-axis so that at any time t greater than or equal to 0, the position is given by said function. So there's your position function. At t equals 0, determine whether the particle is moving to the right or to the left and explain how you know. Okay? So, if we want to talk about is the particle moving left or right, we have to talk about the velocity, yes?
Yep.
Okay. And how do we find velocity? It's the derivative. So x prime of t is also going to be v of t. You can denote it either way. Okay, it's good to make the connection. There's definitely times they want you to make that connection. Are we okay with the basic derivative here? Your derivative agree with my derivative?
Yep.
Okay. And if they're asking you at t equals 0, determine if the particle's moving left or right, then we want to know what is my velocity at 0. And this is where Logan was pointing out. You plug in the 0, and your t values are going to disappear, and our velocity at 0 is negative 12.
Just something that's helpful on like the AP test, since they like to give you absolutely no time to do it.
Well, and that's, as you get better with it, you know, if you can make the quick catches like that, I understand. It also depends how much work they want to show. So particles moving left because
Velocity is negative.
Velocity is negative, or in other words, velocity is less than 0. Okay? I'm going to say moving left, since I'm going to say v of t is less than 0. That's my official mathematical phrase there. Actually, I shouldn't have said v of t. It was at the point 0. So because the velocity at 0 was less than 0, that's what I really should have said. Although we had stated over here that the velocity of 0 equals negative 12. So again, you show all this, you're connecting the dots, and that's what they need you to do. Okay? At what times does the particle change directions?
Find the x-intercepts.
Okay. Particle can change direction when the what? Velocity equals 0. So we're going to take that velocity that we just found, and we're going to set equal to 0. So v of t, which is 3t squared minus 9t minus 12, and we're going to set equal to 0. Okay. Now, make a catch here and make life easy for yourself. Everybody divides by 3. Because it's an equation, can I just drop that 3 out? Yes. If it wasn't an equation, you can't just drop the 3 out. But you can drop the 3 out, or you can factor the 3 out. Either way. Was getting rid of that 3 helpful?
Yeah.
Yeah, because it factors now, doesn't it? Factors into t minus 4 and t plus 1. I might still have my 3 out front, but that 3 is not going to matter. Set each factor equal to 0, and what do we know?
The particle changes directions at 4 seconds because you can't have a negative time.
Okay. So we get t equals 4 and t equals negative 1. The t equals negative 1 does end up being a moot point because it is 0, or a negative, excuse me. Now, with this in mind, It does say justify your answer.
Isn't that what that equation was?
Well, so what we know at that time is that velocity is 0. We haven't technically proved that it changes directions. Does that make sense? We've just said that velocity is 0. Could it stop and then continue the same direction it was going?
Because there's an x-intercept that equals 4.
Well, but again, it's an x-intercept. My graph could do something like that, where it hits 0 and then goes back up. We need to show that there is a change in direction, and a change in direction means there's a change in the sign, yes? Okay, so one way to think about that, we know the velocity at 4 is 0, agree? Find a velocity below that point and above that point. So if I say, for instance, find the velocity at 3 and the velocity at 5.
We don't really, we have a velocity lower than that already at 12 or at 0. So.
Okay, that's true. Could we use that?
Yeah.
Because we don't have it. That's true. Okay, I'll take it. So we know the velocity at 0 is negative. So all we have to show is that a velocity bigger than 4 is positive. So if you plug in 5,
It becomes 75 minus 45 minus 12, which is 18.
Which is positive.
now can we justify that the particle changes directions? Yes, because it changes sign. So at t equal 4, the particle changes directions from left to right because v of t changes signs from negative to positive. So t equal 4, particle changes directions, or direction. And notice it's going from left to right, since sign changes from negative to positive. Okay, so you have to be careful there because we can't just say, hey, it equals 0. We know this particle changes directions. We just know it stops there officially. It could change directions, and that's what you have to show. Okay? C. At t equals 1. You don't need to throw things at Eli.
Thanks.
At t equals 1, the velocity of the particle is, no, not a statement, it's a question. At t equals 1, is the velocity of the particle increasing or decreasing? And explain your answer.
Decreasing. It's a basic polynomial, and we already know when it hits 0.
So I would say, I think it's actually going to increase, but the way I think we justify it is we find acceleration, which is the derivative of velocity, then plug 1 in, because it's the slope of it.
Yeah, so
I
you're,
think it's going to increase because it's going to go closer to 0, if that makes sense, most likely. Not necessarily.
Okay. So, and here's what I'm going to go with. The part I agree with here is the justification is we need to look at the acceleration. Because the acceleration will tell me, is that particle increasing or decreasing at that? Is the velocity increasing or decreasing? Okay. So, I made this bigger so I have more room, so the derivative of velocity is acceleration. And acceleration function becomes 6t minus 9. we do want to know the acceleration at 1.
Oh, you're right.
The acceleration at 1 is -3. As I said, I didn't indicate who was right and wrong there. We need to talk.
Yeah.
I was just kind of guesstimating because it was going to go from
Acceleration.
-12 to 0 eventually, but I didn't know that for a fact.
So, we can say the velocity is decreasing at t equals 1 because the acceleration is less than 0.
Hey, random, but while I thought about it, I don't know if you saw, but Bailey Franklin semi photos are coming out today.
She sent me a message. I have to email her, or I have to send her yours or my emails.
Send her mine too.
I was going to send both. What, did she post it on social media somewhere?
Yeah.
Okay. At t equal 1, is the speed of the particle increasing or decreasing? Justify.
Increasing. Because, I'm going to say, well, I guess the way we can justify it is if we plug in v of 1, we could find the velocity at that point, and we already know that the acceleration, which is probably going to be negative. If the acceleration is negative, it means the speed decreasing.
We already know acceleration at 1 is negative. Sounds like you guys remember the rules. So velocity at 1?
No velocity.
Should be
It has to be.
3 minus 9 minus 12. So we got
Okay. So
-18.
the key is that -18 and -3 are the same sign, right? And I'm assuming you guys remember the rule, or at least I think both of you did, because you both started talking about it individually. That if the velocity and acceleration have the same sign, speed is increasing. If the signs are opposite, speed is decreasing. So my justification here, speed is
both velocity and acceleration are negative.
right. Yeah. So speed is increasing at t equals 1. And the way I'm gonna mathematically say is, since velocity of 1 is less than 0 and acceleration at 1 is less than 0. That's your mathematical statement there. Okay. And I have it referenced because there's some years that we don't remember that fact. I have it referenced to page 144 in my notes. And 144 is where we first learned that fact, I think. Yeah, it's a chart that talks about same sign speeding up, opposite side slowing down. Okay. And E. What is the particle's acceleration at t equals 1/4? And then will ask us to explain the meaning of your answer in terms of the particle's velocity, and how would units be explained in context to the particle. So first of all, they asked us for acceleration at 1/4. Which ends up being
-7.5 meters per second squared.
Yeah. My brain said, yeah, 1.5 minus 9.
15 halves.
So -7.5 or 15 halves, either are good. Okay, unless they have a reason to, get more specific. I have both in my notes. Okay. Explain the meaning of your answer in terms of the particle's velocity. So that's your acceleration. First of all, let's talk, is the particle increasing or decreasing?
In velocity?
Yes, is the velocity
Decreasing.
okay? And I'm going back to explain the meaning of your answer in terms of the particle's velocity. So at time 1/4, we know that the velocity is decreasing because it's negative. In terms of units, do they officially give us any units on this problem?
I thought so. It does not look like it.
No, okay. Because I just have generic units in my notes, so.
I'm just going to use the meters per second.
So, really, part of this I'm just going to say is that particles velocity is decreasing. And of course we know that because the acceleration is negative. And that is at t equals 1/4. Okay. In terms of units, I mean, it's distance per time squared. Are we okay with that idea?
Yeah.
I know Logan is. Yeah, because that's all I have there is that just change, yeah. The units is the distance per time squared. We just don't have those specific units here.
Yeah, no, I was just going to do units per time squared.
Yeah.
D over S or T squared.
Yeah. Hey, I do also, yeah, I have it. I do have D over T squared as one of the options in my notes as well. So, but I think some of what I've written out here is just going through how to get there. So.
Well, we're not halfway through. We've got 10 minutes left.
Well, it is what it is.
Well, if I didn't go all the way to H or something, I mean.
Okay. Well, let's work on 2. Let's see. I don't know. Can we knock out 2? Let's try. Now we're going to talk table. The table gives note what it gives. Table gives the velocity. This time we do have in feet per second of a particle moving along the horizontal axis. The velocity v is a twice differentiable function of time t. Why are they telling me that it is differentiable?
Student can find acceleration.
Because they have to.
I don't know. Yeah.
Differentiability implies that the function is continuous. Okay, so what they're saying, even though they give us just individual values, they have to state, because otherwise these are just points.
Because
Okay.
they have to, otherwise
Well,
you can't do the
we won't be able to answer half these questions if it's not continuous. So just remember, they're saying differentiable. Because it is differentiable, your brain has to say, oh, that means it's continuous. Because if they don't tell us, otherwise those are just like 10 individual points, or however many there are. It's not a continuous function otherwise. So, okay. So they give me time and velocity. At t equals 0, determine whether the particle is moving to the right or to the left, and explain how you know.
So the left velocity is less than 0.
Pretty obvious there. It is, I mean, I don't have anything else. That's the basic gist of what I have, is that I stated the velocity at 0 is -4. That obviously is just pulled from the chart. So we then, of course, know particle is moving left, since velocity at 0 is less than 0. Okay. Okay. B. Is there any time or times during the interval 0 to 15 seconds, which is the whole chart, where the particle is at rest? explain your answer.
I want to say between 2 and 3.
Why?
Because it has to cross through 0. Because
Be-
it's continuous.
Because it's a continuous function. This is why they said that. Okay, otherwise, we don't know because they're just points. Okay, so the first thing I have stated on mine, because what we are technically using, I can guarantee Eli probably didn't know that he was using this theorem, but he just used the intermediate value theorem. Okay, intermediate value theorem is the one that says that, you know, basically, because 0 is between there and it's continuous, then it's going to have to cross through there. Okay, that's the idea. So, I do have on mine stated, I stated that v of t is differentiable. And then I said, thus, v of t is continuous. Okay, that's a good fact to point out. Sometimes you'd be required to, not always, but that is a good fact to point out. If you cite some data, v of 2 is -1, which means v of 2 is less than 0. v of 3 is 1, and v of 3 is greater than 0. So, IVT says there exists a time between 2 and 3 where the particle is at rest.
Let me guess. We gotta do A rock for C.
I don't know, I haven't read C. Not at this moment, so. Okay. C. Use the data from the table to find an approximation for v prime of 8. Explain the meaning of v prime of 8 in terms of the particle motion. Show the computations that led to your answer and indicate the units of measure. Okay. So, yeah, we're going to be talking A-Rock basically. Officially, they ask about v prime of 8. What are we going to have to do?
Find acceleration, which is just A-Rock in this instance, essentially.
And what points are we going to be using?
10 and 7. I hadn't looked at the chart as well.
Okay. We're going to have to use the 10 and 7 because where is 8? 8 is between 10 and 7. So that's going to be your best bet there. Okay. So, because 7 is less than 8 is less than 10, that's why I have, you know, kind of, that's the reason. But yeah, we're going to do v prime of 8. And we're going to estimate that by doing v of 10 minus v of 7 over 10 minus 7. 5 minus 3 over 10 minus 7, which is 2/3. What about a label?
At t equals 8 seconds, the acceleration is 2/3 32. Wait. So how do you?
Okay, wait.
2/3 32 feet. Or
Hold
no,
on.
not the gravitational. What am I doing?
2/3 feet per second.
Yeah, feet per second squared.
Yeah, I was like, wait, what? Why are we making this more complicated than it needs
I
to
saw
be?
feet and
Okay,
yeah.
Square.
okay. Now, what I used is that the velocity is increasing. Okay, that's what v prime of 8 tells me the velocity is, because it's talking about the meaning. I guess it doesn't reference whether we're talking velocity or acceleration, doesn't it? I
It says,
mentioned,
explain the meaning of v prime of 8, which is v prime of 8 is acceleration.
it's acceleration, but it also references velocity. And so I would have said that velocity is increasing. And of course, it's increasing at t equals 8. At, and you can just say 2/3 feet per second squared. We are in feet, right? Yeah. I don't think we can get D and E done in 2 minutes. Dang it. Kind of want to get D done, but I don't think it's going to happen in less than 2 minutes. Well, less than 2 minutes, really, because my watch says 58. So we'll pick up on D and E tomorrow. Remind me if my bin Q gets erased. So we've got what? D and E. We've got 2 more pages.